All right. So it says, surveys 100 people. Okay, I like it. So that is 100. Sample mean time to complete the tax forms, 23.6 hours. One nice thing about not making much money is tax forms take a lot quicker. When you're in a situation where you're not making a lot of money, don't have a lot of stocks, all that kind of shit. That's insane. Oh my God, a full day. There's a known standard deviation of 7 hours. So in section 8.1, we have to know this. Today we're going to learn what we do if we don't know this. So we have to know the population standard deviation in section 8.1. I like it. Where'd it go? Population distribution is assumed to be normal, but we didn't really need that, did we? Why do we not need them to tell us that? N is bigger than 30. Kick ass. Central limit theorem. Chicken, lettuce, tomato. All right. So the first part I basically did for us. Where'd you have trouble? Let's see.
Basically down where it says to make that a confidence interval, I can't get my numbers to line up with what they say the answer is.
Oh, well, there's typos in this sucker. So construct a 90% interval. Anybody 90%? Don't be scared if these numbers start to stick in your head because we're going to use them over and over and over again. 90% was that weird asterisk one. So it's 1.645. So you have to go out 1.645 steps both directions to catch 90%. I like it. So then it says to make a confidence interval. We've already learned 2 of these suckers. We're going to remember the last one we did, the p-hat one. Remember p-hat? If you guys weren't here last time, you're like, what the shit? What were they doing with hats? No, it's a p with a hat on it. And so you just throw everything in there. So there might be a typo in the book. You never know. Sometimes your answers might be just a little bit off because they're using technology to do the work for them, and we're actually doing the work. So sometimes our numbers are a little bit more rounded, but they shouldn't be that far off.
They used 1.96.
Oh, well, that's where they went wrong. So for part D, yeah, it says 90%, so they should have used 1.645. Yeah. So that explains that.
Okay. Also for G, I didn't know how to do that.
Oh. They wanted to be at least 96% confident. Suppose that the firm decided that it needed to be at least, so they want to be more confident to within an hour. All right, so part G's got a couple things going on. So part G says 96% confident. What does that control? What's the level of confidence directly controlled? What did I write up here that had to do with how confident I wanted to be?
Z-score?
Z-score, yes. Right? If I want to be 90% confident, I want to go far enough out to catch 90% of the data. Again, let it be easy, please. If I want to be 90% confident that I caught something particular, how much data should I catch? 90% of it. So if you just go far enough out to catch 90%, you are 90% confident. So that's why the Z-score is directly related. How far out do you go? So for part G, it says 96% confident. Oh shit. How do I figure out the Z-score for that?
You have to look at the chart.
Yeah, look at the chart. Oh shit, you got to do the old-fashioned one. The old-fashioned one. So what's in here?
96.
No way. Okay. So what's out here? 0.02. Kick ass, because 4 total outside, right? Look at the Z-score. And it's asking you, So I desperately want you to understand ideas, but look at the question. The question says, blah, blah, blah. How would the number of people, okay, I want an equation that's solved for n, because they're asking me for the number. So it's going to be this little dude here. And however you want to write that. That little guy we did last time. What's E going to be in this problem? So again, suppose a firm decided to be 96% confident that of the mean length of time to within an hour. How would the number of people change? What would the error be? What's the magic word for the error most of the time? Squeeze? You're all like, what's he doing up there? Sounds like. Within, right? I want to be within so much. It's going to be what the error is. So I want to be within an hour. I'm going to let E be 1. So I was a little bit hidden. But again, what do you focus on? What's the question asking for? That will tell you what formula to use. Then you start to look at what the formula needs and what they tell me. Do they give me enough information to fill in what the formula needs? Okay. Maybe. Is that enough to get you going? Okay. Because I agree, that one you kind of can gloss over the important part and say, what the hell do I do with this? But the most important part was how would the number change? Okay, now I know what formula to use. And the formula tells me what to focus on getting. Z, sigma, E. Okay. Anything else from homework stuff? Yes?
98, H.
Oh, that's just the conclusion we write, right? So the confidence interval you created. H is just say, write the conclusion that we write. We are so and so confident that the interval blah blah contains the, right? I like it.
And 102.
Oh, okay, watch. What's always true about X bar? This is going to be a weird kind of, what's always true about X bar when I make an interval? So if I had an interval from 5 to 9, for the real mean, what was the sample mean?
9.
Huh?
9?
Nope. Where is the sample mean in the interval? Where must it be? Because what did I do to it to create these numbers? I subtracted and added the same thing. So where does it have to be? In the middle. Let that make complete sense. X bar is going to be in the middle of the interval because how do you make the interval? You add and subtract the same thing. So in this case, what would the X bar be? 7. That was easy. If the numbers were uglier, how do you find the middle of any two numbers? You take the average. Yes. Add them up, divide by 2. What's the error up here? How big is the error? 2, because I go up and down. Calm down, Jeff. I go up and down 2, so the error would be 2. So if they give you a completed interval, holy shit, they basically told you everything. The middle's the mean, and then how far away that is from the edge is the error. How do I know that? Because I add and subtract the error to the mean, so that all comes together. Is that okay? Is that all right? Okay. I love that question because you have to think about the problem backwards, and if you know a problem backwards and forwards, you know it. Is the hope. If you came in after I passed stuff out, I got stuff for you, but you can get it later. Anything else from homework stuff? All right. Okay. Anybody need the handout from last time about lengths of dolphins and such? Come over there. So if you missed last time, you got the video to look at. You don't know what the shit this is. But my ultra quick lecture on that is, does this formula look familiar? Yes, I'll answer for you. And then all we did, this was a bit of a talk about how this works, but we normally don't know this. We normally just know this. What is that? What does that mean?
Expected value.
I love you guys. Sample mean. I like it. So I must have taken a sample to get it. So what else has to change on the way then? Standard deviation. And then, so we're using this idea to construct something new. I want to figure out what's the highest and the lowest so that I catch whatever percent. That's really the idea behind a confidence interval. So I want to go up and down a certain number of V's. So this is really just that formula, on steroids or whatever, drug of choice. All right, maybe. Okay, so if they say construct the 95% confidence interval, they have to tell you this and this and this, and then you look that up. And all that is how far do you go out so that you catch 95%? So what would be true about the z-score for 95 versus 99? Which one would be a bigger z-score? The one for 95% confidence or the one for 99% confidence? 99, yes. Because it makes sense. Do I have to go further out to catch more shit? Yes. Right? So of course that one's going to be bigger because I got to go further out to catch more stuff. And the more stuff I catch, the more confident I am I caught a specific one. I want this Pokemon, so I'm going to catch a lot of them, and then I'm more likely to have caught it. I don't believe I just made a Pokemon reference. I'm going to survive. Okay. Maybe you will too. So, I don't want to do another example. We did several. And then we finished this bad boy this side. So if you missed the day, you can watch that lecture again and watch that happen. We got into this last time. We started here again, and we constructed this formula. Big ass P, look at that. Yeah. Anybody remember what the little hats mean? What's the little hats? It's so cute, their little hats.
Percentage, or is the percentage that comes from the
Sample, I love it. Just like X with a bar on it is the average from a sample. P with a hat on it is the percentage from the sample. You might think, what the hell is P bar? Yeah, P bar means something. We'll learn later what P bar means. You walk into the P bar with the P hat, that's a whole day. Okay, so let's try a problem out with this shit. We haven't done that yet. And then I'll let you guys try that other side of that thing. Let me write it back up here. Oh, okay, all right. There's actually kind of a big thing to do here. I don't know if you guys still have this. All right. When I have means, how can I tell if what I'm working with is normally enough? When I have like sample means, how do I see if it's normal enough? Either I tell you it's normal enough, or sample's bigger than 30. You guys with me? So we have something to check when I'm talking about means to make sure that it's normal enough. Cool. I'm not talking about means on this anymore, am I? I'm talking about percentages now. Oh shit. It needs a different test because it's not the same thing. So how can I tell when an NPQ situation, or in this case, NP hat, Q hat, is normal enough? Oh shit. Stay with me. All right. Do you remember that handout? I totally forgot to bring it today. I gave you guys a while back with the flipping a coin, and it had this picture in the middle. And it kind of made sense that the biggest one was 7, because I was flipping a coin 14 times. So of course I expect 7 to happen the most, 7 heads. Okay, maybe. Okay. Does that look normal? Yeah, how can you tell? It looks normal, doesn't it? If you put a little curve on it, it looks very freaking normal. It looks normal as hell, right? One reason why, let me ask you this. Okay. So remember, this was flipping a coin 14 times. So what was the probability of success? And we're talking about getting a head, I think, on that one. 50%, right? And probably failure is 50%. So the mean was 7, which is right in the middle of 0 to 14. Are you guys with me? So it kind of makes sense that the picture should end up being symmetric. Because P and Q are both 0.5. It should be up to the middle and then down. You with me? So that has a very high chance of being normal enough. Now what if instead I had this situation? N equals 14, but P is 0.1. Let's make it even worse. Let's make P 0.01, just to really make this point. Something's going to work up here. Ooh, baby. What do you look like? Ooh, you're both good. All right. I'm easily amused. Help me out. You guys with me? Why was this one at least close to the highest bar? In this case, it was the highest bar. Why was 7 the highest bar on this one? I said it earlier. Why was it the highest bar? Why? Why is 7 the highest bar? What's the mean for this case?
7.
It's freaking 7. And what's another name for the mean? Who said that earlier?
Sample? Expected value.
Expected value. So I expect it to happen. So it should have the highest bar. In reality, the highest bar should be close to it or equal to it, but in this case, it's equal. Let me stop for a second. You guys, does that make sense? If I flip a coin, I expect half of them to be heads. That's the average. If several people flipped a coin 14 times and I average the number of heads they got, I should get 7 or close to it. Or somebody's got a freaky coin, right? Oh my God, they're both heads. All right. What's the mean on this case? In this case, what would the mean be? N times P? What's 14 times 0.01? 14 times 0.01. 0.14. So where should the highest bar be now? You guys can do this, you can do it. It should be 0.14, right? So if I draw this picture, it's going to look like this. It's going to have a really high bar here, and then it's going to go down. Does that look normal? No. I love it. Maybe. So, if P and Q are 50%, that gives it a really good chance to be normal, because then at least it's symmetric, right? If NP is too small, then it doesn't have any chance. It's going to start high and go low. It's not going to start low, go high, and then go low. I really want you guys to get this. If the mean is too small, and I know it starts at 0, because we're talking about binomial shit, you can only have at least 0 people that do something. Then there's no chance for it to go up and then come back down, right? So this is almost too beautiful to believe. You would say that, Jeff. Oh, well. I need to pull the mean out far enough away from 0 so that it's got room to go up and then come back down. So I need for the mean to be at least 5. Because if the mean is too small, it doesn't have room to go up and then come back down. It's almost too easy to believe that that's the check for an NPQ problem. What makes it normal enough? The mean just has to be far enough away from 0 so that it can go up and come back down. That's all. You guys still don't like that. Does everybody understand that the mean is too small and the mean should be where the highest bar is located near? If the mean is too small, that means it starts high and goes low. That ain't normal at all. That's not normal at all. If I made the mean at least 5, now it's got room to build up to it and then come back down. And on the other side, the same thing happens. If the mean is too big. So what we do to make this easier The first part of this should make complete sense. For an NPQ problem to be normal enough, all right, blue. Let me see. This other blue. NP has to be at least 5. And this controls the other side of things. NQ has to be at least 5. Those two together make sure that the picture has the highest bar in the middle somewhere, so it can go up and come back down. So that is equivalent to n greater than 30 for mean problems. For percentage problems, that's the check to make sure that it's normal enough. Normal enough to do what? To get z-scores from confidence intervals, right? I can't use this chart, the z-score chart, unless it's normal. So I have to have a check to know that I'm okay to do it. All right. So I kind of set us up for this earlier this semester when I gave you the z-score chart. I said this is answers. This is an answer sheet. Everybody wants all the answers. I gave them to you. All the frickin' answers. You just have to find them. But you can only use that sheet of answers if you know the distribution is normal enough. So I have to have these tests so that I can determine if I'm allowed to use that sheet. So if I'm talking about means and bigger than 30, then I'm guaranteed that I can use it. For percentages, these two things. If those two things are true, I can use the chart. If one of those things is not true, I'm SOL. I can't do it at all. I will never be so cruel, at least not this semester. Give me a few more years. You never know what's going to happen in a few years. Just going to blow a gasket, just screw everybody. No. But right now, I'm not evil enough, thankfully for you. It took me the right time. To create a problem where the very first step is it's not normal, so you don't have to do any of it. Now, do you understand how that would be really evil?
Yes.
So, on a test, if you think that it's not normal enough and you shouldn't do anything, you still do it. Because more than likely, you're missing something. You still do it. You could say something like, I don't think it's normal, I shouldn't do this, but I'm going to do it anyway. Then you do it. I'm never going to give you a problem on the test where the answer is, don't do shit. If I have a lot of these steps. You guys with me? Maybe? All right. So, let's try a problem out. We talk to 89 people and find, what do you got, Jeff? 11 of them enjoy
Statistics.
Thanks. Sure. I was going to say something political and I thought, no, maybe not. Enjoy statistics. Sure. Yeah, just stick it to Jeff. That's great. Yeah, Jeff. Okay. This feels like I'm not telling you enough information. I got one more thing to tell you, and then we got enough information to do everything. Find the 99% confidence interval for the true percentage of people who like statistics. It feels like very little information. It could be just me. I don't know. I don't have to tell you a lot because once you know p hat, you know q hat. And I have to tell you n to figure out p hat. So it's all like in one, bam, one sentence almost. So remind me again, what's p hat mean, little hat dude? What's p hat mean? Percentage from the sample. So we know what p hat is. Can anybody tell me how to figure out what p hat is?
11 divided by...
Yes, 11 out of 89. Bam, it's the percentage from your sample. That's all the p hat means. So 11 out of 89. It's almost exactly, it's 0.122.
12359.
What is it?
0.12359.
12359?
Yeah.
12359? Okay. I might as well, I could change this rule. Anyway, I'm not going to remember. I say make your P hats and Q hats at least 3 places. And again, you can make them 4 just to blanket. It's got to be at least 3 places. You guys with me? The only thing that's allowed to be 2 places in general is z-scores because the chart only goes to 2 places. Okay. Anybody know what Q hat has to be then? Yeah, it has to be 1 minus this. Remember, no matter what clothing they're wearing, they have to add up to be 1. P shoe plus Q shoe equals 1. They got that equal 1. What's N? We already know what N is. What's N? 89. And what's the z-score I'm going to use? 99%. I showed you guys the little baby chart, right? You're all like, I don't know, man. I don't know if I even brought a z-score chart with me. On your z-score chart, the little baby chart in the corner, isn't 99 one of them?
Yeah, 2.575.
2.575. Does that make sense? I mean, that's pretty big. Are you guys at the point now I can say that a z-score 2.575 is big? Yes? Because where does unusual start normally? Who? 2. And that's over that. So that's a pretty big z-score. It's a pretty big distance away from the middle. So, of course, if I go that far out, I'm going to catch 99%. That makes sense. Because I'm pretty damn far out. Okay, I like it. And now, do I have everything for the formula? Yeah. So P hat, 0.124, give or take, this many standard deviations. Okay. See if you guys can plop that in the old calculator. You do the error first. Is everybody doing that, hopefully? All right, what do you guys get? If you need to borrow a calculator, they're up here, as always.
I got 0.0349.
Coolness. Let me catch up to you. No, you don't. Silencio. Jiminy Jesus. No. Okay. Oh yeah, that's right. Rune, can you turn the, you came in right there, yeah, that one. All right, thank you. Come on, no. I don't want to go further down than that. Let's see how that could possibly help. My Lord, what is happening with you?
Put a piece of paper under it.
Maybe, good point.
0.0349.
Thank you.
I just got this part.
All right, 2.575 times the square root. So the biggest mistake people make here is you put a parenthesis here and then you put a parenthesis. So if you have the old calculator that opens a parenthesis for you, you don't want to close it until you get everything in the square root that needs to be in there. So let's see, times 0.124 0.876 divided by 89. So if you have the newer one, you can tell what's under the square root. That's always nice. It's nice. So I get that. Maybe. So what is that? So I want you guys to realize, if you've ever looked at a poll or anything, a survey, and they give you the results, at the bottom they have that plus or minus 4%. We just figured out how to get that number. Why is this so big? This is like 9%. Why is that so big? 9% off. Holy shit. Why is our error so big? How big of a sample do we take? Is that big? No, Gallup does 1,200 on average sample size. The bigger the sample you take, what will happen to your error? If that number gets bigger, this whole thing gets smaller. So the smaller the sample, the bigger your error. We know that. The smaller the sample you take, the less sure you are about what you find. No? Yes? Maybe? No? We knew that day one. The other thing here is I want to be 99%, so my z-score is kind of bigger than normal. That's not helping either. All right, so how do you make this interval then? You just do this. So we got 0.124 minus 0.09, 0.124 plus 0.09. So we got anywhere from 3.4% to 21.4%. Yeah, we're basically saying we don't know shit here. But can I say that, is this evidence that it's less than a quarter of people? Is that evidence that it's less than a quarter? Is that evidence that it's less than a quarter of people? What's a quarter of people? What percentage is that? 25%. Is that confidence interval we just created evidence that it's less than a quarter of people? Yes, it is, because the whole confidence interval is below freaking 25. Is it evidence that it's less than 20%?
Yep.
Try again.
Wait, no.
Because what's in here is 20%, right? Doesn't it go possibly above 20%? Do you guys see that? So it is evidence that it's less than 25. It's not proof. It's evidence. Is it any evidence that it's less than 20%? No. Because it could be more than 20%, according to my confidence interval. Do you guys see that? No? Please let that be easy. It can't be evidence that it's